Good evening, everybody. Welcome to Chem 1211 with your host, me, Dr. White. Hi, everybody. Welcome to the special Friday night of Chem 1211. All right, tonight I'll be going through the review for test number 1. Let me remind you, test number 1. It will be given this coming Monday, July 1st. Wow, it's already July. Wow, this year is going quick. And July 2nd. And you have to take it at the COD Glen Ellen, not any other testing center. Let me remind you, the testing center is open from 9 a.m. to 5 p.m. in those days. But if you need an hour or more to test, you better get there before they close. So I would highly recommend, if you're going to take it later in the day, try and get there by at the latest 3:30, maybe even earlier. But anyways, also, you will need a picture ID. Since you'll need a calculator, hopefully you got one of these, the symbol, I would recommend you take your own calculator. They have calculators there, but if you're not familiar with the one they give you, that could cause some problems, and you'll need it for test number 1. Now, test number 1 will cover chapters 5 through 10 in the book. And don't forget, in my syllabus, I have a list of the chapter numbers and the titles, so you know what they are. But here I tell you, and you'll find out, this covers chemical bonding, including ionic and covalent chemical bonds. It'll cover mole and mole-related topics, and I think it's 12 points. Oops, gave it away. Balancing chemical equations, so know how to do that. And if you look at the lab on balancing chemical equations on Blackboard, you'll find where in the videos, there are two, actually one major video, you need to review balancing chemical equations. The test has 29 problems on 9 pages. There are no multiple choice, but some of the questions have multiple part, like A, B, C, and so on. And the point breakdown is 49 points for chemical bonds and related topics, and 56 points for mole and mole-related topics, which also includes balancing chemical equations. And if you notice, it adds up to 105. So there's 5 bonus points. Now, what I don't do like other teachers is put a problem at the end, the bonus points, and make it real hard. Nope, don't do that. I just have the whole test add up to 105. So you can pick whatever questions on there you want to be the 5 bonus points. Now, this is important. Like test quiz 1 and 2, test 1 will tell you right under your name, please use proper significant figures for all calculated answers. If you don't, let me center myself a little, that's better. If you don't, I take off a point. Also, please use 3 significant figures for all atomic masses. If you've watched the video, and I'll go through it again tonight, you know how to round off the atomic masses, or also known as atomic weights, to 3 significant figures. If you don't, I'll take off a point on problems that need that. And by this Sunday, I will have your scores in Blackboard, and sometime Sunday, I'll also mail out an individual email, like I did in quiz 1 and 2, or I will do a quiz 2, which I'm going to grade tonight and tomorrow, or the fall next week. And I'll also put out after that, either Monday or Tuesday after the 4th of July holiday and weekend, I will have a Zoom meeting in which I will go through the answers for test number 1. And I'll also mail out your points per question. All right, let's get to work. Now, first of all, if you go to the lecture section of Blackboard, you will see a file cleverly named Chem 1211 test number 1, important information. And I made this originally fall 2022. Wow, that's 2 years ago almost. And it's still valid. This is the material. The last couple of pages of your test will have this. And this way you don't have to memorize it, but you do have to know how to use it. And I would highly recommend you go through and review what's on here and understand it. And that's what I'm going through tonight. Now, if you also go to the lecture section of Blackboard, you will see a file called Chem 1211 Test 1 Review Fall 2022, and it's still valid review for 2024 summer. And let's go through it. Now, as you learned in the last for quiz 2, the atom of all elements has a nucleus with the protons and the neutrons, and all around it are the electron clouds. And the electron clouds contains electrons of different energies. And those energies are designated by shells. And the shells have a very special name. Shell 1, 2, 3, 4 is all we'll deal with. Now, shell 1 is the lowest energy. And this one thing you'll have to remember. And you can come back and I'll be posting this review on my YouTube channel. And as you go down, you go to shell 4 on this table is the highest energy shell. Now, each shell has subshells. In a shell, the electrons have approximately the same energy, but in each subshell, they have the exact energy. And the number of subshells in a shell is right here. And it's real easy to remember. Shell 1 has 1 subshell. Shell 2, 2 subshells. Shell 3, 3, 4, 4. Now, subshells have name, S, P, D, and F, and those are shorthand for the actual names for that, which I now have a mental block. I think F is fundamental. I forgot what S is and all that. But anyways, if we look at this, subshell S is the lowest subshell, lowest energy. F is the highest. Another way of writing it is this way. S is less energy than P, than D, than F. Now, the subshells have a maximum number of electrons that you can put in them. And this will be given to you in the past. Students have to memorize this, but for my test 1, this will be an important information. And subshell S can only have 2 electrons, P6, D10, F14. Why? That's how it came about. That's how Mother Nature, whoever created this, that's how it evolved. Now, let me remind you, as I just mentioned, subshell S is the lowest energy, and F is the highest energy subshell. That means electrons in there are the highest energy for that shell. Now, in my class, one of the ways to say where are the electrons are is by showing the electron configuration. And the electron configuration is a statement of how many electrons an atom has in each of its subshells. And a hint to remember that, at least I do, is numbers, letters, and superscript numbers. And let me open up something I need to open up. So if we scroll back up here, remember you have shells and subshells. And in nature, we always fill the lowest subshell before you go to the next shell. And when you have a subshell, you always fill the lowest subshells of that shell with the electrons. So let's take a look at the following. And bear with me a second. Now, I probably spelled fluorine wrong, so if I did, it's the one element I always spell wrong. Don't ask me why. All right, so we're trying to find the electron configuration or draw it. The first thing is to know that fluorine's chemical symbol is F. Next, we have to know how many electrons fluorine has. And if you look at the periodic table, and this green one is the one they'll print out. It won't be green, but it'll be what you will be given for test one when you take it at the testing center. Here's fluorine, a halogen, and in the upper right-hand corner, the atomic number gives you the number of electrons, 9. So fluorine has 9 electrons. And I like to let the paper do my thinking, so I'll write down 9E to let me know. Now, what's the first shell? And that's 1. And what's 1 only has 1 subshell. And the lowest subshell, let's go back to this to remind you. Important information, the lowest subshell is 1, or shell, and the lowest subshell is here S, and you can have 2 electrons. So let's go back to our whiteboard. So I have 1s, and I can put 2 electrons. Remember, when you write a subshell, it's a number and a letter. So the lowest subshell in F is 1s, and you can put in 2 electrons. Well, I did. Well, I've got 7 more to go because 9 minus 2 is 7. So let's go back to this table, or this one here, same thing. How many subshells does shell 1 have? 1. How many electrons can we put in 1s2? Well, we filled that up. And we filled up shell 1 because it only has 1 subshell. Now we have to go to shell 2, the next lowest energy. and there are two subshells. And we always fill the lowest subshell in a shell, which would be 2s. I can put 2 electrons in there, and I will. So the next shell is 2, and a subshell is a letter, number and a letter, 2s. How many electrons can I put in any s subshell? 2. So I'm going to do that. So 2 plus 2 is 4, but I have to get to 9. 9 minus 4 equals 5 more electrons I have to go. So what do? I go back in case I forgot, and subshell or shell 2 has 2 subshells. The lowest energy is S, and we just 2s, and we fill that up. The next one would be 2p. How many electrons can you put in maximum in any p subshell? 6. Well, our 2p only needs 5. So the next subshell, remember a subshell is a number and a letter. Well, I need 5 more. I can put up to 6, but I only need 5. So the electron configuration for fluorine is 1s2, 2s2, 2p5. All right, next, let's talk about the valence electrons. And the valence electrons, which in Dr. White's mind are the most important electrons in an atom, but that's my personal opinion, are the outermost electrons of that element. You should know what are valence electrons. Those are the outermost electrons of an element. How do you find the valence electrons for an element? You look at the top of the periodic table in the column there. So let's go to a periodic table. And you see I have the numbers in red because a couple of years ago I found out students couldn't read the Roman numerals, like what is IV above carbon? That's the Roman numeral 4, or V is 5, and VII is 7, and so on. So I wrote the the decimal number up there. So you students who didn't learn, like almost all of you, Roman numerals, you now know. I think I learned them in 2nd grade or 1st grade that we were taught that, but we were taught the Roman numerals. Now, if we look at any element in a column, the number on top tells how many valence electrons. If you look at any element in a column, you're going up straight and up and down in the periodic table. You see hydrogen, lithium, sodium, potassium have 1 valence electron. Magnesium, calcium 2. Go all over here to my favorite element, carbon, 4 valence electrons. Nitrogen 5, oxygen 6. By the way, sulfur also has 6, which is in the same column. The halogens, fluorine, chlorine, bromine, iodine, have 7. And the noble gases, helium, neon, argon, krypton, xenon. Remember, krypton in our universe is not a green solid that kills Superman, but it's a colorless gas. They all have 8 valence electrons. The maximum number of valence electrons an element can have is 8. So if I were to ask on a test, how many valence electrons does calcium have? Well, you know, calcium, Ca, up here 2. If I were to ask how many valence electrons, oh, one of my favorite, chlorine, it's halogen, Cl, and above the number is 7, so it has 7 valence electrons. Now, one way to show for an element its valence electrons is called the Lewis structure, sometimes called the dot structure. I like to honor the chemist who came up with this, Dr. Lewis, and we call him and you only use the chemical symbol for that element, and you only use valence electrons. And you put one valence electron on each side before you double up. Put two on the side. Remember, if you write the symbol, it has four sides. Sometimes when I write a test, I'll write give, others show. And it might be a multiple part, one part. I don't know, let's pick one. Bromine. And bromine's chemical symbol is Br. But now we first of all have to find how many valence electrons bromine have. And if we look at the periodic table, you see Br, you go all the way to the top and you see the number 7. By the way, that's the way I write my 7. The one in red, I picked that up in high school from our German teacher who was from Germany. I thought that was the coolest way to write a 7. I've been doing it ever since. But anyways, bromine has 7 valence electrons. So just to remind myself, I'm going to write this here. And you start with a dot on each side. And now we have 4, 1 on each side. Now we double up. How many? Well, 3 more, because we have 4. We have to show 7 dots. 1 more there, there. Now, this is one way. You could also write it this way. And because I have a piece of paper at home signed by the Board of Regents of Michigan State University that says I know how to do this, my PhD degree. And that's how you do the Lewis structure. And there are 2 others I could have wrote. 3 sides have 2 dots, 1 side has 1. And that's the Lewis structure for an element. Now we start getting into the good stuff. And that's chemical bonds. And chemical bonds are the forces that hold elements together in things we call molecules, like water. And there are 2 types of chemical bond. You should know. I don't know if you saw in my videos, but I can be very subtle. See how subtle I can be? All right, you should know, what is an ionic bond? It's a bond that results from the transfer of 1 or more electrons from one atom or group of atoms to another atom or group of atoms. That's an ionic bond, because that's the transfer of 1 or more electrons from one atom or group of atoms to another atom or group of atoms. Now, covalent bond is different. That results from the sharing. If we were in a classroom, you'd see me doing this, holding hands or forming a link like this. By the way, this is how a knuckle coupler on a train cars looks. And Dr. White loves trains. He's a model railroader and loves taking trains when I was in Europe. But anyways, back to chemical covalent bonds. It results from the sharing of 1 or more pairs of electrons, and that's important. Pairs of electrons between 2 atoms. So ionic bond, transfer 1 or more electrons from one atom or group of atoms to another atom or group of atoms. Covalent bond, results from the sharing of one or more pairs of electrons between atoms. Now, I'll never ask you what the octet rule is, but in compound formation, atoms lose, gain, or share electrons in such a way that their electron configuration becomes identical to that of the nearest noble gas to them in the periodic table, which means 8 valence electrons. So atoms, except for hydrogen, that's the only exception, the octet rule is 8. They want to have 8 valence electrons on their own by losing, gaining, or sharing electrons. Now here, when you have an ionic bond, that's the coulombic or charge attraction between two different ions. And ions have a charge on it, either positive or negative. So one of the things you should know how to do is determine or write what ion does the following element form. Now here I have an example with calcium. If I were to ask you, what ion does calcium form? Now there's shortcuts, but this way is foolproof because I don't like shortcuts because you have to memorize something and you wonder, did I get it right or not? Doing this, that. This is foolproof. First, you need to know how many electrons and protons calcium has. How do you find that out? You go to the periodic table. Calcium, number of electrons and protons is the atomic number, and calcium is 20. Now, next you'd have to determine what's the nearest, meaning closest numerically by atomic number to calcium, the noble gas that's nearest. Now, krypton is at 36, which is 16 away. Argon is at 18, that's only 2 away. And the one that's closest has the smallest difference in atomic numbers, which is argon. Then you have to look at how many electrons argon has, 18. So first we have to determine how many electrons and protons the element has, in this case, calcium 20. And then what's the closest noble gas? Remember, that's the one all the way over to the right with 8 valence electrons, argon. And how many electrons does argon have? 18. So how do we use that information? Well, calcium wants to have the same number of electrons as argon to be stable when it forms an ion. That's 18 electrons. Now, you're not going to lose protons, not in chemistry on this planet. And therefore, you have 18 electrons, now 20 protons. Now, each electron has a -1 charge. Each proton has a +1 charge. Do the math, -1 times 18 is -18. +1 times 20 is +20. Add them together, and that will show you the charge on the ion. And that's a +2. Now, if I ask you to draw the ion, you have to show both the symbol and the charge, which is superscript. Now, the old way, which Dr. White still prefers, is the element, then is it plus or minus and the number. The newer way is the number, the element, then the number and plus or minus. You can do either way on my test. And since it's a +2, this is how you show it. Now, when we talk about forming ionic compounds, we have to consider charge balance in ionic compounds. And the formula of an ionic compound, its chemical formula, indicates the number and kind of ions that make up a compound. The one thing you should remember, I'm going to be subtle again. I can spell it. The sum of ionic charges in a formula is always zeros. All molecules have a net zero charge. So what does this mean? Let me rephrase this. I probably would write it this way. And it might be multiple choice, or not multiple choice, multiple part. And let's say what would be, give the empirical formula. That means the chemical formula, simple chemical formula for a molecule with the following ions. Let's do this one, calcium +2 and bromine -1. And this has a +2 charge. This has a -1 charge. This always has to add up to 0. It doesn't. Well, you can't change the charge, but you can change how many of that element is present in the molecule. For this to add up to 0, you need 2 bromine, because 2 times -2 is -2, and +2, that adds up to 0. So what does this tell you? You need 1 calcium, because the number in front is 1, and 2 bromine, and we show that this way. Again, 1 calcium, 2 bromine from this, what we just determined, and this would be the formula. Now, I think at some point during, I forgot which lecture, I talked about polyatomic ions, and let's look at one. Same question, give the empirical formula for a molecule with the following ions, and the same concept. This is a magnesium +2 cation. Cation means plus charge, anion, negative charge. Now, this is a polyatomic ion. 2 or more atoms held together by both, you'll learn later on, covalent and ionic, or covalent, that has a charge. And here, the charge is called the hydroxide ion, anion, and is a -1. All molecules have a net 0 charge, so this has to add up to 0. It doesn't. To get it to 0, you need 2 of the hydroxide, OH-, and 1 magnesium. Well, how do we show that? Well, 1 magnesium, when you have a polyatomic ion and you have more than 1, you put a bracket, OH, which is the polyatomic ion. You don't show charges. And then subscript outside to the right of the bracket, you put the number you need, 2. And that's magnesium hydroxide, 1 magnesium, and 2 OH or hydroxide anions. And you should know how to do that. And now, when we talk about covalent molecules, molecules made up of covalent bonds, you have two types of electrons in those type of molecules. Bonded electrons, those are pairs of valence electrons that are shared between a covalent bond, and non-bonding electrons. Those are a pair of electrons that are not being involved in electron sharing. Now, when we talk about a covalent bond, there are three types. I think I better be subtle again. See how subtle I can be? And the three types are a single bond, double bond, and triple bond. Single bond, double bond, triple bond. And you should know a single bond is a bond between two atoms that share one pair of electrons. A double bond, remember single is one, double bond is a bond between two atoms that shares two pairs of electrons. And you should know that. Double, two. And a triple bond is a bond in which two atoms share three pairs of electrons. So you should know, single bond, a bond in which two atoms share one pair of electrons. Double bond, a bond in which two atoms share two pair of electrons. And a triple bond, a bond in which two atoms share three pairs of electrons. Now, unlike a Lewis structure of an element, if I were to ask you to draw the Lewis structure for, and I give you the formula, hydrogen sulfide, and that's the sulfur atom. Well, first of all, you have to find how many valence electrons each element or atom in there has. And if we look at hydrogen, we go to the top of the column, hydrogen has one valence electron. Sulfur, S, look at top, has 6. That's one valence electron, not the word hive. And this has 6 valence electrons, VE valence electrons. Now, in order for this to work, sulfur has to be in the middle, and it is. By the way, hydrogen sulfide is that stinky gas you sometimes smell from I haven't been to one in years, the forest reserves where they have the hand pumps and the water smells stinky. That's it. Or if you ever have hard-boiled eggs, after you take the shell off and you open it up and it stinks, even though I like hard-boiled eggs, it still stinks. That's hydrogen sulfide, H2S. Now, sulfur has 6 valence electrons. So I'm going to do that, Lewis structure, one on each side. Now, hydrogen has 1. So I'm going to put 1 over here, and the 1, hydrogen says, I've got 1 valence electron, you've got 1 valence electron, let's share. And they do. And the other side, the second hydrogen, H2, I have 1 valence electron, you had 1, let's share. Now, it's time to check if we did it right. And you use the octet rule. Stable molecules which have only covalent bonds, have each element have an octet. The one exception, the octet for hydrogen is 2. So if I look here, this hydrogen, shared and unshared, has 2. This one has 2. They're happy. Now, if we look at sulfur, shared and unshared, if you count inside the blue circle, 2, 4, 6, 8, it's happy because it has its octet 8 valence electrons, its own and shared. Now, let me rewrite that again because I want to show you something else. Pair of electrons being shared. What kind of bond is that? A single bond. Same thing here. And those are bonded electrons. Now, if you look on sulfur, you'll see there's not 1, but 2 pair of electrons not involved in the chemical bond. And those are non-bonded electrons. Now, there's something I should teach you, and I will. I didn't. If we look at the periodic table, elements excluding hydrogen in the first column, the alkali metals, and the second column, the alkaline earth metals, never, ever form covalent bonds. The alkali metals and the alkaline earth metals never form covalent bonds. They always form ions. They give up their electrons. So what does this mean? Again, draw the Lewis structure for and a very important chemical in our daily life in the chemical industry is sodium hydroxide. And if I were to ask you to draw the Lewis structure, first of all, how many valence electrons? Sodium, if you go to the periodic table, look on top, you'll see has 1 valence electron. Oxygen has 6 valence electrons. Dr. White knows these by heart. Hydrogen, 1 valence electron. Now, remember what I said. All alkali metals form an ion. And what ion do the alkali metals form? A +1. Well, the oxygen has 6 valence electrons. The hydrogen has 1 and says, let's share. And if you look at that, we say, oh, we're done. But wait, if we look here, oxygen only has 7 valence electrons, shared, non-shared. That can't be right. What happened to this valence electron from nitrogen, which it lost to get to Na+, the cation? It goes here to the oxygen. Now, this polyatomic ion has an extra electron and has a negative charge. And that's how you do molecules that have either the alkali metals or the alkaline earth metals as one of the elements in there. That's always going to be positive. I'm a positive ion. By the way, these always form, if you know 1 in a column, you know them all. Lithium, sodium, and potassium always form a +1. Magnesium, calcium, +2. And same thing for the halogens, they all form the same ion, -1. All right, let's get on to my favorite area, moles. And we're not talking about the little furry animals that dig holes in the ground, moles and mole calculations. You should know, what is a mole? A mole is a chemist counting unit. And there are a number of important mole relationships you should know. 1 mole of an element, and this is Avogadro's number. You should know that's Avogadro's number, name of the great Italian chemist, Avogadro. I don't know if back then they actually called him chemists. But anyways, 1 mole of an element equals Avogadro's number. And I think I corrected it. Hopefully I did on test number 1. Let me correct it now. That should be superscript. And that should be superscript. So 6.02 times 10 to the 23rd atoms of an element. 1 mole of a compound, like water, is 6.02 times 10 to the 23rd molecules of that compound. And at the bottom here, if you've been watching my videos, remember to use your good buddy, your good friend, unit analysis. And it's been my good buddy, my good friend since high school when I was taught that by Mr. Salners, who was our teacher. I still remember his name and his face, did a great job. And let's look at some problems doing this. All right, let's say you were given a problem. How many moles HBr, and it's hydrobromic acid, you'll learn later in the semester what an acid is, are 7.31 times 10 to the 36 molecules of hydrobromic acid, HBr. And if you've been watching my video, you know when I approach a word problem, relax, take a deep breath. You can do this. You write down what are you being trying to find, and I use a question mark, moles, HBr. Then underneath I write, what am I given? Well, the only thing I'm given is this. And now, once I've done this, I never have to look up at the word problem because I've got everything I need. The only thing I have to start with is this. If there's some kind of conversion ratio, what units do I want my answer to be in? Well, we figured that out right here. Well, how do I proceed? Well, it's time to use your good buddy, your good friend, unit analysis. And how do you use your good buddy, your good friend, unit analysis? Whatever I'm trying to get to, the units go on top of the ratio. Whatever I'm trying to get to, the units go on top. whatever units I start with, the units go on the bottom of that ratio. So I'll write that in. And now, where do I get these numbers that go here? Well, what units are we dealing with? Moles of HBr and molecules of HBr. And if I go to important information, test number 1, you'll see right here, 1 molecule of a compound equals Avogadro's number. And whenever you have two things equal, A equals B, there are two relationships or ratios you can always have. A over B, and it's not equal. They're different relationships. So I'm going to use the word and B over A. So 1 mole of a compound equals Avogadro's number of molecules of that compound. So 1 mole of a compound equals Avogadro's number of a compound in molecules, 6.02 times 10 to the 23rd. So now, before I pick up my calculator, before I do this, I'm going to look at, notice molecules of HBr divided by molecules. Anything divided by itself equals the number 1, meaning it cancels out. What units am I left with? Moles of HBr. Is that what I want my answer to be in? Yep. So I'm on the right track. So I'll now pick up my calculator, turn it on, clear it, put in 7.31 blue double E 36 divided by Avogadro's number 6.02 blue double E. That's if I do exponential in my 23, hit equal, and my calculator gives me this number. I'll write it down here. This. Remember, you should use proper significant figures for all calculated answers, which is what you're doing here. All non-zero numbers are significant, so that's 3 significant figures. Now this 1 is part of the definition, 1 mole, and that's an exact number and plays no role. Avogadro's number is a significant figure number, and this one has 1, 2, 3. 3 significant figures. And I think if you looked in the video, you'll see years ago, I found this site that had 17, Avogadro's number to 17 or 18 significant figures. Why would you need that? I don't know, but somebody thought they did. All right. So when you multiply and divide, you get the same number of significant figures as the number that has the fewest significant figures. When you multiply and divide, you get the same number of significant figures as the number with the fewest significant figures. Well, in this case, they're both the same, 3, 3. So I have to round this off to 3 significant figures. Keep the 1, keep the 2, keep the 1. That's my 3 significant figures. I used a 4 to round off. Is that 4 or less? And it is 4. And therefore, this and everything else here in this first number I drop. And the correct answer using proper significant figures would be 1.21 times 10 to the 13th moles of HBr. All right, let's do another one. Let's pick on hydrogen sulfide again, that stinky compound. And the question is, how many grams? G is grams. Grams is a measure of weight. How many grams hydrogen sulfide, H2S, are in 7.654 moles of H2S? So what are we being asked to find? I put a question mark and then write that. Units, and in this case, the molecule. How many grams of H2S? What are we given? Well, we have 76.654 moles of hydrogen sulfide. So once we have this right here, we never have to look at the written word problem again. And now the only number I have to start with is this. If I had some ratio that I could convert moles of H2S, hydrogen sulfide, what units do I want my answer to be in? Well, we figured that out right here. We want grams. Let me make a better G. That's a better G of hydrogen sulfide. And how do we proceed? It's time to use your good buddy, your good friend, unit analysis. My favorite siren whistle. Company that made this is no longer in business. I've got 4 of them. They never leave my house. They're very valuable to me. And how do you use your good buddy, your good friend unit analysis? Whenever we're trying to get to, the units go on top of that ratio. Whatever we're trying to get rid of, the units go underneath. And now I'll write that in. And where do I find those numbers? Well, let's look at important information. Test number 1. We have hydrogen sulfide, a compound. And we're trying to find the relationship between moles of a compound and grams. Grams is a weight. And here we have 1 mole of a compound equals the molecular weight of that compound in grams. What's molecular weight? Oh, good news. It says right here, the molecular weight of a compound is the sum of all atomic weights. So we know for every 1 mole, we need, and I'm going to use abbreviation, the molecular weight in grams. Well, how do we do that? The molecular weight of hydrogen sulfide is the sum of all atomic weights. And hydrogen sulfide has 2 hydrogens and 1 sulfur. And what's the atomic weight? The hydrogen, remember on test 1, it will say use all atomic weights to 3 significant figures. And if we go to our friendly neighborhood periodic table, hydrogen here is 1.008. You keep the 1, keep the 0, keep the 0. You use 8 to round off. That's 5 or higher. Drop that, the number in front. You increase by 1. So the atomic weight to 3 significant figures of hydrogen is 1.01. And if we look at sulfur, it's 32.066. Remember, chemical symbol sulfur is S. To round that off to 3 significant figures, because if you don't, I take off a point. Keep the 3, keep the 2, keep the 0. The next number, the first 6, you use to round off. Is that 4 or less or 5 or higher? And hopefully I'll pick 5 or higher. So I'm going to drop those 2 6s. The number in front, I'll increase by 1. 0 becomes 1. So the atomic weight of sulfur to 3 significant figures would be 32.1. Do the math. 2.02, 32.1. Add these together. Now, I didn't cover this earlier in the semester, but in the videos I did when I showed you how to calculate molecular weights. And that is for addition, you get the same number of significant figures to the right of the decimal point as the number that has the fewest significant figures to the right of the decimal point. And all numbers after decimal point are significant. So this has 2 significant figures. This has 1. And therefore, your answer, when you do an addition, should have the same number of significant figures to the right of the decimal point. In this case, and it has the lowest, the number you get when you add should have the same number of significant figures to the right of the decimal as the number you add that has the fewest significant figures. Let me say that again. When you add numbers together, the number with the fewest significant figures tells you you should have the same number of significant figures in your answer to the right of the decimal. So we keep the 1 because we need this 1 significant figure. Use the 2 to round off, that's 4 or less. We drop that. So the proper significant figures, the molecular weight of hydrogen sulfide, you know, that stinky stuff, is 34.1. If you haven't guessed, I'm having a good time because Dr. White loves mold problems. They're very important. So now I'm ready to pick up. No, I'm not ready to pick up my calculator. I'm going to look at the units. Notice moles of H2S divided by moles of H2S. Anything divided by itself equals the number 1, meaning it's canceled out. What am I left with? Grams of H2S. That's what I want for my answer. I'm on the right track. And now I can pick up my calculator, clear it, put 7.654 times 34.1. And my calculator gives me this number. And let's take a look at this. When you multiply and divide, you get the same number of significant figures as the number with the fewest significant figures. All non-zero numbers are significant. This is 4 significant figures. This is 3 significant figures. This is an exact number. Therefore, our answer should have 3 significant figures. 1, 2, 3. Use the 0 to round off. It's 4 or less. So I drop all this. And our proper answer using significant figures is 2.61 times 10 squared grams of H2S. And that's how you do that. Now, important word to the wise on your test, when you have a word problem like that, show your work. If you just write down the answer, and if you were to write down 2.57 times 10 squared grams H2S and not show your work, that's wrong. I'll give you 0 points. This were 6, 7, or 8 point problem, you'd get 0. But if you show your work, especially this, and you got that wrong answer, and I can say, oh, you knew what you were doing. You just did something wrong with your calculator. And I would take off only 1 point for a math error. So it always pays to show your work. I'll say that again. If you just write down the answer, and it's not the right answer, I will give you 0 points. And this may be an 8 or 10 or 7 point problem. If you show your work like I just did, and you made some sort of math error here, say it's an 8 point problem, I would give you 7 points. So it always pays to show your work. And if I look at the clock, this is going a little longer than an hour, but hang in there. I want to go through everything slowly. Now, the important thing using moles is called mass calculation for reactions. If you have 2 reactions, speaking about reactions, I better do this because I don't see it. I have it here on the review. Let's talk about chemical equation or reactions. We show that by here, A plus B arrow C. And what this means is A and B react at the head of the arrow to make C. A and B are called the reactants. If you come from the chemical industry, we also call them starting materials. And C is the product or products. An important thing is balancing a chemical equation. And to balance a chemical equation, you have the same number and same type on each side of the chemical equation of the elements. And you can only change the coefficients, the number in front. Now, some advice I'll give you that's always worked for me, leave hydrogen, oxygen last. Do all the other elements and balance them first. And remember the even odd trick. Now, since I've been going pretty long tonight, I'm going to ask you to go to, and let me show it to you. Let me go into student view. Assignments. If you look at the balancing chemical equation lab, lab 7, you'll see watch the videos. To learn how to balance chemical equations, watch the first one starting at 22:48, 22 minutes, 48 seconds. And that way you'll see how to go through what I'm teaching here, how to determine its balance. By the way, if I ask you to balance an equation on a test, you're going to have to balance it. The answer, it's always balanced, will never be a correct answer on any test I give. Again, if I ask you to balance a chemical equation, you're going to have to balance it. The answer, it's already balanced, will never, ever be correct on my test. And test number 1 is one of my tests. Hint, and you'll learn all this. All right, let's move on. We have 2 more sections to go. And the second to last is called mass calculation for reactions. And let's open up the problem set. This would be the best way for me to do it. All right, sorry it took a while to find it. All right, let's look at the following. This is from Chapter 8, Practice Problems. And for the following reaction, 10 points each. 10 points for this one. For the following reaction, hydrogen plus chlorine gas give hydrochloric acid, HCl. Now, in this molecule, the number in front of each chemical is called the coefficient. Those are exact numbers. When there's no number there, it's the number 1. Now, let's look at this problem. You're given a chemical reaction that's balanced. And I'll always, when I took it, you have to balance it first. I don't do that. It'll be balanced. So we're asking how many grams of H2 are needed to make 125.6 grams of HCl. And this is a mass calculation. Mass is grams for reactions. And you need 3 steps. Remember, mass in this class means grams. Step 1, convert the mass of A to moles of A. Step 2, convert the moles of A to moles of B. And finally, step 3, convert the moles of B to mass of B. So you need to do these 3 steps. This will be given to you on test number 1 in the back. So let's go back to that problem. So the first step, we need to convert, first of all, what are we being asked to find? Grams of hydrogen. What are we given? Grams of HCl. First step, this is A, convert grams of A to moles of A. And once again, use your good buddy, your good friend, unit analysis. We're starting with 125.6 grams of HCl. We're going to moles of HCl. Whatever we're trying to get to goes on top of a ratio to make this conversion. Whatever we're trying to get rid of goes underneath. Where do we get a relationship between moles and grams of a compound? Remember, we just did it. 1 mole of a compound equals the molecular weight of that compound in grams. And the molecular weight is the sum of all atomic weights. So here I have hydrogen. There's only 1. Here's the atomic weight, the 3 significant figures. For chlorine, it's 35.5. Remember, round off the 3 significant figures. Add it up. Remember, when you add up, you get the same number of significant figures in your answer to the right of the decimal as the number that has the fewest significant figures to the right decimal. 101 is 2 to the right of the decimal. 35.5 is 1 to the right. So this should be 1. Keep the 5, drop the 1, because that's the one you round off with. That's 4 or less. So we have this. Notice grams of HCl divided by grams cancel out. And we get a number. This is a multiplication division. 4 significant figures. 1 is an exact number. It's part of definition. And the 36.5 is 3 significant figures. And you get this number. Step 2, you go from moles of A to moles of B. Well, we're trying to find grams of hydrogen, and we're trying using moles are HCl. So let's take a look at this. And now the coefficient, the number in front, gives you a molar relationship. When there's no number, it's the number 1. And this relationship is, for this balanced chemical equation, 1 mole of hydrogen reacts with 1 mole of chlorine to make 2 moles of HCl. Again, the coefficient, the number in front, when there's no number, that's the number 1, gives you this molar relationship. 1 mole of hydrogen reacts with 1 mole of chlorine to make 2 moles of HCl, hydrochloric acid. So we want to start with moles of HCl, which we calculated in 1. We want to go to moles of hydrogen, because eventually we're going to convert that to grams of hydrogen. And you use your good buddy, your good friend, unit analysis. Whatever we're trying to get to, the moles go on top of the ratio. Whatever we're trying to get rid of, the moles go underneath. And where do we get a relationship between moles of hydrogen and moles of HCl? The balanced chemical equation. 1 mole of hydrogen makes 2 moles of HCl. 1 mole of hydrogen, so we put a 1 there, makes 2 moles of HCl. These are exact numbers. They do not play a role in significant figures. So this is 3 significant figures. To the math, you get 3 significant figures. Are we done? No, because up here we figured out we have to go to grams of HCl, and now we do step number 3. And that's now convert moles of B, what we're trying to get, hydrogen, to mass of B. And here we have figured out moles of hydrogen in step B. Hold on, I'm getting my alphabet numbers mixed up. Hold on, I got to reboot. Nope, I'm rebooted. We want to go from moles of hydrogen to grams of hydrogen. And therefore, we have our ratio. Use your good friend, your good buddy, unit analysis. Whatever we're trying to get to goes on top of the ratio of the units, grams of H2. Whatever we're trying to get rid of goes underneath, moles of H2. And where do we get that relationship? 1 mole of a compound equals the molecular weight of that compound in grams, and the molecular weight of that compound is the sum of all atomic weights. And H2, there's 2 hydrogens. And the atomic weight, the 3 significant figures for hydrogen, is 1.01. We rounded it off to 3 significant figures. And since there are 2 hydrogens in H2, molecular weight is the sum of all atomic weight. We have 1 mole equals the molecular weight of hydrogen, grams. That's 101. Do the math, that's 202. And moles divided by moles of hydrogen cancel out. We're left with grams of hydrogen. We're on the right track. This is 3 significant figures, 3 significant figure, exact number, and you get 3.47. Now, as I mentioned a number of times in my videos, when you have a multi-calculation or step problem like this, there are 2 ways of rounding off. One is at each step, and the other is at the very end. Dr. White is a round off at each step person, but I'm not going to force you to do my way. So you might have learned it differently elsewhere. I do calculations for both ways, and sometimes they're the same, sometimes they're slightly different. And if they're slightly different, either answer will be the same, which is why I also have or 3.48. And you should know how to do this problem. Wow, look at the clock. This is a long review, but it's a test, not a quiz. And the last thing you should know is about limiting reactants. If I were to have, say I make the stylus for my tablet that I'm using to write on, one pen, one cap. And if I only have 5 of these, but 10 of these, how many total units can I make? Well, if I only have 5 of these, or 5 of these and 10 of these, this is going to run out before this, and you could only make 5. Well, the same thing happens in chemistry. And let's take a look at a and for limiting reactants, you determine, whoops, hold on, I just did something. For limiting reactants, you determine the number of moles of product produced by using the moles of each reactant, and the lower number of what you produce is the number that you could make. Now, I'm going to only do it in moles. You could do it in grams. That just gives you a lot more work, and I'm not going to be cruel. I think still the Supreme Court has outlawed cruel and unusual punishment to students. I don't know what is Supreme Court. Oops. But let's take a look at a problem. Here's one. Let's look at number 10. Again, this is chapter 8, practice problems. You're given a reaction. For the following reaction, how many moles of carbon dioxide, CO2, are made when you react 2.35 moles of C3H8 is propane, C3H8, with 10.2 moles of oxygen gas, O2. So what are we being asked to find? Moles of CO2, which is why I have my question mark. What are we given here? Moles of C3H8 and moles of oxygen. And when you're asked if you have this much of this and this much of this, how much of the product, this is a limiting reactants. And you need 2 steps. What you'd have to do is find out how many moles of each, using each reactant, can you make if all of it reacts with to make the product you're interested in. So for C3H8, we have 2.35 moles of that, propane. We want to find out how many moles of carbon dioxide, CO2, will make. Well, you use your good buddy, your good friend, unit analysis. Whatever we're trying to get to goes on top of the ratio. Whatever we're trying to get rid of goes underneath. Where do we get these numbers? Relationship between moles of C3H8 and moles of CO2 from the balanced chemical equation. Remember, the coefficients gives you the number of moles for each reactant and product in the balanced chemical equation. And when there's no number, it's the number 1. And this reaction tells us 1 mole of C3H8 makes how many moles of CO2? 3. 1 mole of C3H8 makes 3 moles of CO2. These are exact numbers. Do the math. Remember, moles of C3H8 divided by moles of C3H8 becomes 1. Cancel out. We're left with moles of CO2. Then we got 705. Now, you also have to figure out how many moles of CO2 would oxygen make. In this case, 10.02 or 10.2 moles of oxygen. How many moles of CO2? Again, use your good buddy, your good friend. Oh, that came out weird. Unit analysis. And moles of CO2 go on top of the ratio to convert moles of oxygen to moles of CO2. Whatever we're trying to get rid of goes underneath the ratio, moles of oxygen. And where do we get these numbers? From the balanced chemical equation. 5 moles of oxygen make 3 moles of CO2. 5 moles of oxygen make 3 moles of CO2. 5 moles of oxygen, 3 moles of CO2. These are exact numbers, though moles of oxygen divided by moles of oxygen cancel out, become number on. We're left with moles of CO2, so I set it up right. And this, the 3 significant figures would be this. Now, for these limiting reactants, you look at 1 and 2 here. The smaller number is your answer. In this case, 7.5, and that's how you do it. And with that, I'm done. Wow, we just had a long evening, but you people are worth it, really. So don't forget, on Monday and Tuesday, July 1st and 2nd, from 9 a.m. to 5 p.m., you better get there before they close, long before, you will take test number 1. Bring a photo ID. Bring your calculator. Also, I'd highly recommend, you can use pen. I wouldn't on my test. Use a pencil or mechanical pencil. They don't no longer make these, but check this out. Is that wicked? These, I've had this one since, I think about 25 years ago. I bought a bunch of them. And bring a good eraser. The white ones are the best. Now, because normally if you were in my class face-to-face, you'd have 55 minutes to do my test. And most students are done in about 45 minutes or so if you've studied. However, since you're in the test center and you have distractions going, people coming in and out, finishing tests, I've given you 2 hours. Thank you, Dr. White. You're welcome. You have 2 hours, so you'll have plenty of time if you have studied. And with that, I'm done for evening. I'll stick around for a couple minutes if anybody has any questions, but you know how I'm going to end it. I'm going to say in Yiddish, it means go in health, gain gesund. COVID is still out there. In fact, I just read there's a new variant that's starting to hit everywhere this summer. Hopefully you're vaccinated. I'm fully vaccinated and I still wear my mask. I'm careful, but gain gesund. And goodbye now. I stole that from Granny into Beverly Hills. Bye now.